So I've put together here a variety of additional topics that I think are very interesting, potentially very useful for you if you actually begin using LEAP in practice. We don't have time to cover them in depth in the workshop, but think of this as an introduction. I'm going to point you to, I'll demonstrate a few things, I'll give you an overview, and I'll point you to some resources that you can use on your own to follow up on and to learn more about these topics. So the first one is about exporting and importing data. And in general, what I've done is I've arranged these. There are some basic modeling features that I've put first, which aren't related to any particular sector in LEAP. Then there are some demand side features. Then there are some reporting features that I'll be highlighting. So just in terms of basic modeling tools within LEAP, the first thing that I'd like to call your attention to is exporting data to and importing data from Excel. This is a capability that you can access within LEAP under the analysis menu, as shown in this screenshot. And what it allows you to do is to export either expressions or variable values from your model and put them into a specially formatted LEAP formatted spreadsheet. And then if you have a LEAP formatted spreadsheet, you can import expressions or values from that spreadsheet into your LEAP model. And when you put these two things together, they become a very powerful tool for bulk loading data into LEAP models. That could include bulk loading of expressions into LEAP models. The pattern that gets used is that typically you would set up your branch structure in LEAP. You would do an export that would create a LEAP formatted spreadsheet for you with whatever values are in the model at that moment. You could then revise that spreadsheet by copying and pasting data from other sources or writing formulas in Excel to get the expressions that you wanted. And then you would import the spreadsheet back into LEAP. And I'll show you an example of this in a second. You're going to see that the data or the expressions in your spreadsheet are segmented by branch, variable, scenario, and region. And then I've also put in the last bullet here one warning, which is that when you work with a LEAP formatted spreadsheet, by default, LEAP hides some columns that have identifiers for branches, variables, scenarios, and regions. And if you sort the data in your spreadsheet, you should make sure to unhide and sort those columns so that you don't break the correspondence between certain data in the spreadsheet and where LEAP thinks those data should be put. So let's look at a particular example of this. So here I have the Fredonia model, and I'm in the current account scenario. And let's say that I want to revise what's being put in here for exogenous capacity. So I'm starting by clicking on the branch that I want to export from, which is the processes branch. I'll go to the analysis menu, and I'm going to choose to export to Excel. Now, LEAP brings up a box that has a number of different export options. This allows you to control what's actually being exported. First, you can choose to export for a particular branch that you select right in this window, or you can export for the branch that you previously clicked on in the tree, that's processes and below, or you could export all branches in the model. Similarly, you can choose whether you want to export for the currently selected scenario, which is current accounts or all scenarios, the currently selected variable or all variables. And then also whether you want to export expressions, so that's what's in the expression box here, or whether you want to export the data, which is what the expressions translate into when you convert them into time series data. And if you do export data, you can choose to export data just for selected years, the base year, the first scenario year, and the end year of the model. If you are exporting expressions, which is what I'll do in this particular example, then you can choose if you want to export all expressions in that scenario, just the expressions that are inherited from other scenarios, or just those expressions that are inputted directly into that scenario. So that would be whatever is in blue text. I'll say, for the sake of argument, that we're going to do all expressions. And then LEAP We'll provide some additional columns in the spreadsheet that represent different levels in the tree. By default, it gives you 8 levels, which is sufficient for this tree. It doesn't go more than 8 levels deep. If I were exporting from a very deep tree structure, I might change that number of levels. So when I hit OK, I get a spreadsheet that looks like this, where Leap is showing me for branches, variables, scenarios, regions, certainly in the units that are being used, the expressions that are actually put into the model. And then there are level columns out here for filtering, if I want to filter to look at particular subsets of this spreadsheet. Now notice that the spreadsheet begins with column E. So columns A through D are hidden. And if I unhide them, I can see that they are internal Leap identifiers for the branch, variable, scenario, and region. And so if I wanted to do an overall sort of this spreadsheet, it really should unhide those columns, choose all of the data, and then do a sort on the data if I want to do that. So please do bear that in mind. If I didn't have these columns selected and I just sorted the columns from E forward, then I might end up putting expressions in the wrong branches. So in this spreadsheet, then you can modify the expressions directly. And you can say, you can put in a new expression like interp base here. Anything you can write into the expression window in Leap, you could put here. And then you can re-import this spreadsheet into Leap. Now, when you do the importing, this is similar to the importing of yearly shapes that we discussed earlier. When you choose to import from a Leap formatted Excel spreadsheet, Leap will look for the most recently active spreadsheet you had on your computer, and it will try to pull the information from that spreadsheet. Now, in my case, it doesn't matter because I just have one spreadsheet open. But if I had multiple spreadsheets open, the right practice would be to start in the spreadsheet that I want to import. So bring that up in Excel, then switch to Leap, then choose Import from Excel. And when you choose this, you get to optionally specify whether you want to bring the information from the spreadsheet right into Leap. That's the data option here. Or whether you want to create a link to the spreadsheet, in which case it would use an Excel linking function like what Charlotte just demonstrated for the Leap Weep integration. That would allow you then to maintain the data or the expressions in that Excel spreadsheet afterward. And anytime you change them in Excel, they would be updated in the Leap model. Most of the time, you'll use this first option, which is to import data. That's going to take the content in your spreadsheet, bring it into Leap. There's also an option to limit the replacement, the overwriting of information in the model right now. So you would only replace constants, interp, step, and smooth expressions. Those are rather simple expressions. I always just deselect this because when I prepare a spreadsheet that I want to import into Leap, it has the information that I want. So I want it brought in regardless of what happens to be in the model already. And then there's further an option to match by names of branches, variables, scenarios, and regions instead of by IDs. If you're following the pattern that I've just showed you, where you start by exporting something from Leap, you mark up the spreadsheet and you re-import it. You don't need to worry about that. This would be if you created your own spreadsheet with columns for branch names, variable names, and so forth. So if I hit OK, you can see that it pulls in my new expression and it brings it in and validates it right on import. If it had a problem importing, it would tell me about it. And then I could go and check that problem and deal with it. A very good practice if you're using this feature within Leap is to save your model before you do an import. Then if you don't like the results, you can just discard the unsaved changes. Just to show you very quickly what it would look like if I did an export, but in this case, and I'm going to switch my scenario so it'll have the projected values as well. If I do an export to Excel, this time for the baseline scenario, the exogenous capacity variable, and I choose values for all years rather than expressions to export. Then you end up with columns for all of the years and the data, the results of your expressions for those years. And if you want to change this and bring it back into Leap, you can do that. You can override values in particular years. You could change this to 1,000 here. It's going to be 1,000 from this point forward. And you can choose in this method column what function you want to wrap these numeric data in during the import. So by default, it's interp, but you could take any other time series expression like step or the data function, which we looked at briefly the other day. And you could type that in this column here, and Leap would use that when you did the import. So this is a way that you can really manipulate individual values and individual years rather than writing your own expression. So a very, very useful feature within Leap. And practically, if you are building a model, you'll end up using this all the time. Let me move on to couple of other overall modeling capabilities. So this first one is about custom input variables. We've already seen key assumptions, and I've mentioned that they're custom input variables that you can put into a model. And those key assumptions get added to the top level key assumptions category or top level branch in the tree. You can group your key assumptions within folders. There's no limit on how many key assumptions you add to a model. And when you add the model, you have to specify the unit. Or when you add a key assumption, you have to specify the unit for that key assumption, but it becomes a custom input. There's another way of adding custom inputs to Leap as well, and that's called user variables. I don't think we've gotten into this in our workshop so far, but the capability is there, and it's not hard to use. User variables can be added through an option in the analysis menu, or by right-clicking on the variable tabs when you're at a particular point in the tree and choosing to add a user variable, like in this screenshot here. So this is, again, just a custom input variable. With user variables, you have several properties that you can define, including the unit, the description for the variable, and other things. But notably, you also have visibility properties that control where the user variables are displayed. So you're adding them to a particular point in the tree, and you can limit them to that point in the tree or to other similar types of branches. So for example, you could have a user variable that was visible for all non-energy sector category branches. There are a number of different filtering options that allow you to control where user variables show up in your model. You can add up to 400 user variables per model. And at some level, they're not that different from key assumptions. They happen to be stored in a different place. They show up in the tree rather than in the key assumptions branch, but they're both custom inputs. In both cases, you're defining the unit. Leap does not do unit conversions for you. In both cases, you can populate the input variable with whatever expression or data you want. Usually, people in practice, they use key assumptions for cross-cutting inputs. So those are variables that are needed in multiple different parts of the tree or multiple different sectors, like population or GDP. And usually they use user variables for variables that are really only needed in one branch or a few branches, so in a limited part of the model. Let me show you quickly. I've shown you already today a user variable. I created this one called demand side interest rate, or a key assumption. Let me show you an example of a user variable. So suppose I was modeling household lighting, and I decided that I wanted to add a variable here for, say, the number of bulbs per household. And then I'm going to calculate the demand cost based on that. So I can come to the analysis view and I can choose to add a user variable here. Or I can right click on the variable tabs and I can add a user variable here. And then I give it a name. I have to give it a unit, and I can give it a description. Over here, I can choose where I want this to be visible. And I'm going to say that I want it visible for demand technologies at a particular place in the tree. So they're going to be demand technologies within the urban lighting branch. So now Leap adds a new tab for me for number of bulbs. And I can put a number in there or an expression in there, and then I can reference this variable elsewhere in my expressions. And if I go to some other part of the tree, like electric stoves, I should not see number of bulbs. So a couple of options for putting in custom inputs. Right, there's a question about how can you add more than 400 user variables? No, you can't. There's no option to do that. It's just a limitation within the software. If you have more than 400 that you need, then put them in as key assumptions. And remember that you can always put, for key assumptions, you can always put your key assumptions into folders. So if you want to, and in most models you would, have folders for different sectors assumptions. You could have a folder for the residential sector, right? You could have one for the commercial sector, for the power sector, and then you can have even additional folders within those. So it's easy to divide up and classify your key assumptions so that when you look at the key assumptions branch, the list is not overwhelming. And that's what you would have to do if you actually needed more than 400 user variables. All right. Moving on. I talked about custom inputs. Let's also talk about custom outputs. So these are custom result variables that you can create in a Leap model, and they're called indicators. You can turn them on under basic settings, scope and scale. There's a checkbox for indicators. And when you do that, Leap it adds one more top level branch to your tree called indicators. And then within that, you can create folders and output variables as you like. Now, indicators have a special privileged position in Leap modeling. Normally, when you define an expression for a variable in Leap in the analysis view, normally you cannot refer to contemporaneous result variables in your expression, which is to say, you can't refer to results from the same year in the expression for an input variable, because that creates a circularity and Leap can't deal with that. Leap, when it's doing its calculations, it calculates 1 year at a time. So if I wanted to have, for example, the level of capacity for a particular electricity generation process be dependent on the level of industrial final energy demand in the same year, I wouldn't be able to do that easily within Leap. That's a reference to a result variable in the same year, and Leap doesn't allow that, except for indicators, because indicators are a special category, and Leap calculates them last after calculating all of the rest of the inputs and outputs for a year. So in this case, for indicators, you can have direct references, that is, contemporaneous references to results in the same year. In other cases, since you can't reference result variables in the same year in your expressions, normally what people do is they use lagged references, which lag by a year or two. So that's the advantage of indicators. The disadvantage of indicators is, depending on how much you're incorporating in an indicator, and in particular, if you're referencing a lot of result variables in an indicator, they can be slow to calculate. And so if you find that's the case, and you're working with the model, it's taking a while to calculate because of the indicators branch, you can always turn off indicators, again, in basic settings. When you do that, any indicators that you've defined are saved, the expressions are saved, your branch structure is saved, They're just not calculated when you calculate the model thereafter. And if you turn on indicators again later on, then the indicators will come back and you'll be calculated again. So let me show you an example of working with an indicator. I have, at this point, taken this model fairly far afield. So I'm going to actually, this is my Fredonia model. I'm going to just revert to the end of the cost benefit exercise. We'll take that as a starting point for what we're going to do. So this is a model now of energy supply and demand, emissions, costs. And I want to turn on the indicators branch here. Okay. So let's say I want to have as an output, I want to have per capita greenhouse gas emissions from my Fredonia model. So I could add an indicator for that. I'll just choose to add a new branch here. And I'm going to call it per capita GHG emissions. Now, because this is a custom output, I have to specify the number of, or the unit that I'm going to use. And I'm going to say it's going to be tons of CO2 equivalent per person. And now it's up to me when I put my expression in to make sure that I manage my units properly so I actually end up with tons of CO2e per person. But let's try to do that. And I'm going to put in one expression that's going to apply to all scenarios. And therefore, I can put it into the current account scenario. And I'm going to choose to work in the Builder tab, so I've got a bit more room to work. So in principle, what I should have to do is take a result variable, which is greenhouse gas emissions, and then I should divide it by population. And so I'm going to take total greenhouse gas emissions for the entire model, which is a result variable that would ordinarily show up in this top level branch Fredonia. And then I'll divide it by population, which is a key assumption. So I'll use the branch and variable selector to do this. I start by choosing Fredonia, hit the next button, and it shows me a number of different variables I can access. Some of these are data variables, these are inputs. Some of them are result variables. And the one I'm interested in is this one here, 100-year global warming potential. And I want to have it come out in tons. So I'm going to choose metric tons as my unit. And then I want to divide this by population. So I could do the branch and variable selector, or I could do what I like to do, which is drag and drop. This is coming in as million people, and I don't want that. I want this to be tons per person. So this should be the expression that I want. And I'm going to try to submit this and see if it takes it. And it looks like it did. So good. So far, so good. Now with an indicator, if I look at the table right now, I don't think I will see any results. With an indicator, you have to recalculate results in order to see results for the indicator. So I'm going to do that. Let me save this, and I'm going to choose to look at my results. Now, if all went well, and I click on the indicator here, I can see per capita greenhouse gas emissions. And I should be able to see that for my different scenarios now. So this is now in tons of CO2 equivalent per person across my different scenarios. And this looks reasonable. I've got in my baseline scenario, it's the highest level. In the mitigation scenario, it should be the lowest level. And this gives you a sense of how this model is performing on that indicator. Really, the scope of action for indicators is very broad. You can do a great many things with them. There's a question here. If I want to create a time series analysis on the result to create changes over time from the base here, how can we do that as an indicator? So that can be done as well. And that could be done just in the result view. There's no need to create a separate indicator for that. Base year here is 2010. When I look at the more options here, I should have an option to do, for example, indexed results. So this takes the base year as 1 and shows me how these change over time. So emissions are going up in all cases, but least in the mitigation scenario here. Right, now let's look at some specific demand-side modeling methods. Some of these we've alluded to earlier in the workshop, but I'd like to just provide a little bit more information about them. The first one here is something that folks asked about the other day, which is demand-side load curves. So far, when we've been putting load curves into our models, we've been using supply-side exogenously specified load curves for an entire electricity module. And that's one way you can do it, but you can also have LEAP calculate the total system-wide load endogenously using curves that are attached to individual demand technologies in LEAP. I mentioned the other day that this is enabled through basic settings under the calculations tab. There's an option to have load shapes calculated for each demand device. When you do that, LEAP will add a new variable on the demand side of the model called load shape, as you can see in this screenshot. And then that load shape can be populated with a yearly shape or other time sliced data that show how the total annual energy demand is divided among the time slices in the model. When you turn on load shapes for demand devices, you'll have an additional option in LEAP to restrict it to electric technologies only, as that's the most common use case for this feature. Let me show you an example here of this. I'm going to take you to a different model here. This is another training model that we have. This is of a small country's energy system and includes energy and non-energy emissions here and energy system modeling. And I want to just call your attention to two different scenarios. So we have a number of scenarios in here, but there's one scenario that's a baseline business as usual scenario, and then there's one scenario that involves electrification of private vehicles. Right now, the load shapes are being calculated for the entire system. So that's under the electricity generation module. I can see if I look at the load shape variable, it's this system-wide load curve that's used. And it looks like we have, for time slices in this model, we have 96 time slices. For wet season, a dry season, with a weekend day and a weekday and 24-hour resolution for each day. So let me just start, without doing anything further, just start by calculating these two scenarios. So what I'm looking at here is a graph of road transportation, final energy demand in the electrification of vehicles scenario. This is the electric vehicle scenario and differences versus the baseline scenario. And I'm showing a view by fuels. This view tells you essentially what's happening between the differences between these two scenarios. There are more electric vehicles in this mitigation scenario, and this creates an overall increase in the use of electricity, a decrease in the use of gasoline. The decrease in gasoline outweighs the increase in electricity because the electric vehicles are more efficient. So right now, it's assumed that these electric vehicles consume electricity in the same way as the rest of the overall system. That is to say, and if we put some time slice names here, you can see they're using most of their electricity during daytime hours on weekdays. That's the assumption here. That's the overall system-wide load curve that we have. And so when they increase electricity demands, which they do here, we can see the differences in electricity output. They increase demands by about 100 gigawatt hours. it's assumed that those new demands are added to the system at the normal times of high demand for the rest of the system. But that might not actually be the case. In fact, what could be likely is that electric vehicles might be implemented with particular incentives for charging to try to get them to charge during off-peak times. And we can represent that with demand-side load curves. Let me show you, I have to close some Excel windows here. I'll show you a spreadsheet that provides one example of that. So here I have some load shape data for electric vehicles where I've imagined that electric vehicles are charging during overnight hours. So people drive them during the day, but they plug them in mostly at night and during the overnight hours when the other demand on the system is low. So I have here a set of 8,700, I'm sorry, I have time sliced data here. I have here a set of 96 hourly data points. And I'm going to import them into LEAP as a new availability shape, which we can then attach to electric vehicles. So I've come to the yearly shape screen, and I'm going to choose to import from a time sliced shape. And it takes the most recently open Excel worksheet, which happens to be my EV worksheet. And there's a named range in there for my data points, and I can then import these. Oops, I don't want to do this. I want to create a new curve. So this is going to be called EV charging. I'm going to specify that it's a load shape. And here I can do my import. So this is how this set of data actually looks. You end up with the charging happening during the overnight hours and no charging during the daytime hours, as an example. I'll close this window and then turn on the demand side load curves. Again, under settings, calculation. And now I want to turn it on for each demand device, and I'm only going to show the load shapes for electric technologies. So when I come to the demand technology branches, I can see that there is now a new variable called load shape. And here I can choose my new EV charging load shape. And I'll do the same for electric motorcycles. In the meantime, I want my other electric demands elsewhere in this model to have a baseline load shape that corresponds to the overall system load shape. So I need to make sure that that's done as well. By default, LEAP brings in this load shape variable with a value of 100. That's not actually going to be useful for this case because I need to have a time sliced value. And so what I'm going to do is choose a branch that has the load shape variable. I'm going to switch to the current account scenario because I want to affect all scenarios in the model. And I'm going to use that export-import capability that we just looked at a minute ago. Exporting to Excel for all branches in current accounts, the load shape variable. I want expressions, and I want all expressions. So this shows me everywhere that there's an electric technology in my demand model and where that load shape variable is activated. And so I'm going to choose to use the default load shape for all of my electric technologies except for the electric vehicle technologies. So that should be this expression, yearly shape demand. Here are my electric vehicles, and I'm going to replace those with EV charging, which I believe was the name of my other shape. So the assumption is that all of the road electric vehicles charge using that new profile. And I'm going to bring this back into Leap by importing from Excel. Now I should find, if I look here, that I've got EV charging as my load shape for electric vehicles, electric motorcycles, and any other electrics in the road transport sector. So now we're having the same amount of electricity production that's necessary. But we can see, if we look at the power generation curve, and I look for one of the years of my projection. If you compare what's happening in the baseline to what's happening in the electrification of private vehicles, the shape of that curve is changing. We could see this quite clearly if we look at differences between the two curves. I want to see overall dispatch here. So this is showing me how in the EV scenario versus the baseline, there's much higher charging now, or much higher power demand that's coming in overnight hours. If I look at the table, I can see that as well. So in those overnight hours, not sure why it's restricting to one. Let me just, I think this is an erroneous label here that Leap is showing, because in fact, this is the total charging for the entire system. But the EVs have added this extra demand now in the overnight hours, as opposed to just slotting it in to wherever the system-wide load curve would have suggested. So it's a bit of an integrative example that shows how you can use that demand-side load curve feature and actually implement it in practice with importing and exporting of results. This particular model we're looking at also has transport stock turnover modeling in it. I mentioned this earlier in the workshop, and I'd just like to provide a bit more information about it and give you some pointers for where you can look for more information too. So this type of modeling is enabled with transport technologies, and you can choose to set up a transport technology when you're building your demand model. Those are the technologies that have the little wheel icon. And essentially what happens when you do this is Leap will allow you to specify the starting stock of vehicles, how vehicles retire, how many new vehicles are sold each year, and then it will track the vintages of vehicles, where the vintage is all vehicles that are sold in each year and how many of them remain. The size of a vintage in any given year depends on the initial number of sold, the time elapsed since the sales year, and the survival profile. When you do stock turnover modeling, you can specify a probabilistic profile that indicates when vehicles when they may retire, how likely they are to retire by a particular date. You can specify the starting stock. In addition, you can specify its age distribution. So LEAP will know how quickly the starting stock is expected to retire. And fundamentally, then, when LEAP runs and does its energy demand calculations, it calculates energy consumption based on the number of vehicles, their fuel economy, so how much fuel they use per kilometer or mile traveled, their mileage or their distance traveled, and their fuel shares in the case of multi-fuel vehicles that consume, for example, ethanol and gasoline together. Now, a key advantage of this type of modeling, in addition to just being able to explicitly track how vehicles enter and retire from the fleet, it also allows you to model the evolution in certain vehicle characteristics over time, notably their fuel economy, the distance that they're traveled, and their emission factors. So it's expected as vehicles age that they start to wear out. Their fuel economy goes down. They also are usually driven less, and their emissions profiles usually become worse. So all of those characteristics can be modeled as a function of the age of the vehicle. Stock turnover modeling also gives you some variables for simulating scrappage. And that would be a way that you could force the premature retirement of certain vehicles. And it's really useful for examining policies that target new vehicles, like emission standards, fuel standards, the introduction of particular technologies, or emissions that target the scrappage of particular types of vehicles, or policies that target the scrappage of particular types of vehicles. This approach allows you to see how those types of policies propagate through the vehicle fleet over time. When you do stock turnover modeling, you have to think about how the characteristics of new vehicles could evolve, and that's specified in variables like the fuel economy variable for LEAP, but then also how the characteristics of vehicles change as they get older. You can, again, specify those changes for emission factors, fuel economy, and distance traveled. Those are specified by special life cycle profiles, which is another type of curve you can enter into LEAP. Then finally, you should consider how specific policies might affect stocks in future years by having a certain number of sales of vehicles or a certain scrappage or replacement policy. Life cycle profiles are set up under the general menu in LEAP, under the analysis view. Right alongside yearly shapes, there's an option for life cycle profiles. And again, they're used to describe how certain characteristics of vehicles change as they get older. They typically start from a value of 100%, which is the characteristic of a new vehicle, and then they either increase or decrease from there. So here we're looking at a degradation of PM10 emissions from vehicles. It's a curve that describes that. New vehicle emits 100% of the new vehicle amount. As it ages over time, the emissions go up according to this curve. These profiles can be specified using data points. You can draw your own curve, or you can use an exponential function within LEAP, or you can import points from Excel. And when you look at the results of stock turnover modeling, you get a few additional output variables, which I've shown here. You can show some results by vintage. It's this multicolored picture here. Point of which is to show you that certain vintages, when they start out, they have more vehicles. Over time, their number of vehicles decreases. You can also see explicitly the sales of new vehicles, the stocks of vehicles on the road at any particular time. And you can get a summation of the total distance traveled as well by type of vehicle or vintage. That's in addition to the variables that you normally get out of a LEAP demand model, like energy demand, emissions, and costs. Now, everything I've said for vehicle stock turnover modeling more or less the main principles apply to other types of stock turnover modeling. Remember, there's a vehicle stock turnover capability, and then there's also capability to add. I'd have to add it in a new branch here, but to add it a technology called, I'll show you here. And other technology with stock turnover. So you can use that for simulating stock turnover for appliances, for example. And these basic principles that I've talked about here, the types of outputs you can get, stock modeling and sales modeling, they apply as well. In the case of the other technology, you don't get vehicle-specific variables like the distance traveled. Let me move on. I know we're coming close to the end, and I want to share several other things with you. I'm going to start talking a little bit about some reporting features. So the first is another view in Leap that we haven't talked about very much so far. It's the overviews view. You get to that in Leap by clicking on the overviews button here. I'm going to just reopen my Fredonia model and do that. So the overview screen is essentially a dashboard. It shows you the results from multiple saved reports in one screen. Those are our favorite charts that you can save when you are looking at the results view. And you can optionally include sliders for key assumptions that you want to have. And then you can hold a slider and see what happens if GDP or population or some other key assumption changes, and it will regenerate all the charts for you. When you put an overview screen together, you have a number of options in terms of the charts that you're showing, the scenarios that you're showing, and other things. All of this is available within the Manage Overviews window here. So here you can choose what you want to show, how you want to order it. The point of overviews is to facilitate stakeholder engagement, to show some critical results from a model that you could then bring up on screen with a group of stakeholders, and you could explore them together. For very large models, overviews can take a while to calculate. And if you have sliders in an overview that would cause it to recalculate, that could take a while as well. So if you have a large model, the best thing to do if you want to have overviews is to pre-calculate the model, and then you can show the overview screen to users or to stakeholders for different scenarios. The next reporting option I'd like to touch on, and this will have to be fairly brief, is marginal abatement cost curves. Some of you are probably familiar with these already. The purpose of them is to show the cost and abatement potential of different mitigation options on a single graph that can be used to help prioritize the implementation of those options. So typically they plot emission reductions, cumulative emission reductions versus some reference scenario against the incremental cost per unit of emission reductions, such as dollars per tons of carbon dioxide equivalent. And again, the incremental costs are calculated in comparison to some reference scenario. Max can be set up to discount both costs and emissions. Usually the costs are discounted, the emissions are usually not discounted. And if you look at a MAC for any given set of options, the area enclosed by the MAC gives you the cumulative cost of the options. If you're looking at a MAC like this example here, anything that is a bar below the x-axis is a negative cost option. That means it's an option that should, in principle, create cost savings according to the analysis. And the options are usually ordered from least expensive to most expensive, which makes it easy to prioritize measures. You can just choose to take measures up to a certain cost per ton of emission reductions, for example, and make that your top priority measures. So MACs are a helpful way of considering the results from emission mitigation studies. This is a quick slide on cost discounting, which I'm not going to dwell on, but you can look at it, it shows the mathematical formulation for discounting costs to account for the time value of money and the fact that costs incurred in the future are not considered to be equivalent to costs that are incurred today. The problem with MACs is that if you have a set of measures, those measures may overlap. And if they do overlap, you have to decide how to resolve those overlaps. The classic example of this is an energy efficiency measure and a clean energy supply measure. So imagine that we have a measure for residential electric efficiency by implementing more efficient air conditioning systems, for example. And then we have a measure for renewable electricity. And if those measures are implemented in conjunction, then the efficiency measure will not give you as much emission reductions as it would if you implemented that by itself without the renewable electricity. And so there's an interaction between these two measures. And if you're going to put them on a MAC and think about adding up their total emission reductions, which is what a MAC does, then you have to figure out how to resolve those interactions. And there are three basic ways that this gets done, which are outlined here on this slide. The first option is called a partial approach. And here I'm using terminology from a UNFCCC publication on greenhouse gas emission mitigation assessment methods. This is an older publication, but the principles are still hold today. And it introduces a set of terminology that's useful for thinking about these approaches to resolving dependencies on a MAC. So in a partial approach, what happens is you just look at each mitigation option separately versus your baseline scenario. You figure out which one is the cheapest. According to that comparison, you put that on the MAC first, then you put the next cheapest and so forth. But the options are ranked independently, and therefore this ignores possible interdependencies or overlaps among the options. So it's simple to do, but you end up with emission reduction potentials that aren't really additive and probably should not be shown on a MAC together. The second option is called the retrospective approach or the retrospective systems approach. And so basically what happens here is that the options are first evaluated independently versus the baseline. The most cost-effective option is assumed to be implemented. And all of the remaining options are recalculated, assuming that the first option is implemented. And the second most cost-effective option is added, and so forth. So this is a way of assuming that options are implemented in order of their cost efficiency, and that the incremental emission reductions that you get can be calculated on that basis. It doesn't capture necessarily how later options could affect the emissions of cheaper options that are assumed to be implemented earlier. But it is a self-consistent and widely used approach. The third approach that gets used is an integrated energy system optimization approach, which simultaneously takes into account the interdependencies within a system and then can allow you to generate a MAC curve by varying an overall carbon price and seeing how much additional mitigation you get at different carbon prices. LEAP itself supports the first two methods. And those two methods are supported. I'm going to bypass this slide and just focus on this. They're supported with a capability to generate MACs in LEAP's summaries view. This is another view that you've already looked at in the cost-benefit exercise. In the summaries view, you can add your own summaries, and you can add one for a MAC if you want to. In order to do that, you have to specify what the baseline scenario is that you're measuring against. And you have to have separate, freely combinable scenarios for each measure that you want to plot on the MAC. And again, when I say freely combinable, I mean that you should be able to add them in without any conflicts between them. You can designate which scenarios are included in a MAC in the Manage Scenarios window, and LEAP's help system goes into this. And you can define multiple MACs in a model. with different emission variables and cost variables for each one. So you can have a MAC for greenhouse gas emission reductions or for, say, sulfur dioxide emission reductions or some other emission variable that's of interest to you. You can then choose when you calculate it whether you want to calculate using the partial method or the retrospective method. The retrospective method takes longer to calculate because you have to look at many different iterations, possible combinations of the scenarios. And the results can be viewed in graphical form like you see here or tabular form. This is a nice feature, and it's a feature that people have been using LEAP to generate MACs for a number of years. It's a feature that you used to have, or it's a process you used to have to do manually, and now LEAP can do it for you. And it's nice to be able to push a button and walk away and let LEAP do all of that work in the background to generate that MAC.